Let's recall Coulomb's law. Coulomb's law essentially describes the electrostatic force that 2 point charges feel as a result of one another's electric charge. So let's suppose we have the following 2 stationary point charges, one given by lowercase q and a second one given by uppercase q. If we know the distance between them is given by lowercase d, then we can use Coulomb's law to solve for the electrostatic force, which is given by the product of the charge of point charge 1 multiplied by the charge of point charge 2 multiplied by k, our constant, divided by the distance between them squared. Now we can also replace our k by using the permittivity of free space, which is given by epsilon naught. So this equation is also equal to lowercase q multiplied by uppercase q divided by 4 pi epsilon naught multiplied by d squared. Now notice, in the same way that the force of gravity is a force that acts over a distance, electrostatic forces are also forces that act over a distance. In other words, even though these 2 point charges aren't actually physically touching, there is still a force, and this force is a result of the electric charge which acts over a distance. Now, early scientists and early thinkers had a problem with visualizing how forces can act over distance, and a British scientist by the name of Michael Faraday came up with a way to essentially help us visualize how this takes place, and he came up with a concept known as the electric field. So, any electrical charge creates an electric field which extends outward and permeates all of free space. Now, if a second electric charge is placed in this electric field, that charge will feel a force as a result of electric field. So let's suppose we have the following charge given by positive uppercase Q. Now this positive charge will create an electric field, and the field lines will extend outward in all possible directions. One such field line is given by the following green arrow. Now if we take a tiny positive test charge given by lowercase q and place it along the line of this field line, this point charge will feel a force as a result of this electric field. Now we define electric field as the force that this point charge will feel divided by the charge of this electric charge. So our E is equal to force divided by Q, the charge of this particular point charge. Now, we can also define our electric field in terms of Coulomb's law. So notice force is equal to this quantity. So we can replace this force that we got in this equation with the following result. So our force is equal to K multiplied by lowercase q multiplied by uppercase Q divided by D squared. And then we have the Q that comes from this equation. Notice the Q's, the lowercase q's will cancel out, and we're left with K multiplied by uppercase Q divided by D squared, the distance between them squared. Now we can also replace this force with this equation, and we get the following result. So this is our equation for the electric field for any single stationary point charge as described in the following case. Now notice in both of these equations the lowercase q does not appear. So that means that the electric field that this charge creates does not depend on the charge of this point charge. So this E is independent of what this charge creates. So if we look at the following result, if we look at this equation, we can now determine the force on any point charge Q as a result of the electric field. So if we take this equation and rearrange it and solve for the force, we see that the force that any point charge feels is equal to the charge of that point charge multiplied by the electric field that is created by the other point charge. So, let's look at the following example. Determine the magnitude and direction of electric field at some point A 50 centimeters away from point charge Q that has a quantity of -6 times 10 to the -6 coulombs. So here we have our charge Q, and we're trying to calculate the electric field at this point A, a distance of 50 centimeters from this charge. So we essentially want to use the following equation. So electric field is equal to Kr constant multiplied by the charge Q divided by the distance squared. So the distance is 0.5 meters, so we square that. The K is 8.99 times 10 newtons times meter squared divided by Coulomb squared, and the Q is given to be this quantity. So we multiply, divide, and we get about 2.2 times 10 to the 5 newtons per Coulomb. Now notice the units of the electric field are newtons per Coulomb. So, now, this is the magnitude of the electric field. Just like force, electric field is a vector. It also has direction. So, in this case, notice our electric field pointed outward, away from this point charge, and that's because it had a positive charge. Now, if it has a negative charge, as in this case, the electric field will point towards this point charge. So if this was negative, this would point in reverse, and it would attract this point charge. So that means this points towards this charge. So if we place a positive test charge in this location, that test charge will attract towards this Q as a result of this electric field.